And really towards the end last time, we really started talking about stoichiometry and specifically solution stoichiometry. And really, as we talked about, between stoichiometry, really any stoichiometry, solution, gas, regular stoichiometry problems, they're really the same steps along the way. And obviously, as we've gone over a number of times, we always want to start with a balanced equation. We want to convert to moles. We do want to be on the lookout for limiting reagents, if applicable here. Then we want to figure out the limiting reagent. We then want to do our mole to mole relationship from the equation. We then want to convert those moles to some other units. Is typically the steps that we follow pretty much in any type of stoichiometry problem. With solution stoichiometry, there's a couple of differences. It obviously will usually involve molarity and volume. So usually the molarity equation is used somewhere along the way or in multiple spots. So instead of doing our grams to moles like we typically will do, and you can still do it. We did a couple of examples, I think, last time where we still sort of do that. We could also use the molarity equation and take moles times molarity. Remember that molarity is moles per liter, so that those guys cancel out when you multiply it by them. The middle part's really the same. Remember, regardless of the sort of type of stoichiometry, whether it is, thank you, it is regular stoichiometry, gas, solution stoichiometry, the way that we know if we do need to sort of determine a limiting reagent is if we have enough information to get to moles of each of the reactants. So a lot of times in the case of solution stoichiometry, if you look at it and you have enough information, molarity and volume for each guy, you typically will need to figure it out. You'll figure out the limiting reagent like we did obviously previously, same sort of effect there, our process. If it's not a limiting reagent problem, then it's probably a basic sort of stoichiometry problem where you just convert to moles and then you skip right on to the mole to mole relationship between the two things that you're interested in from the balance equation. And really at the back end, multiple things are usually in play. Moles to grams is obviously still a very common ending, but using molarity as well on the back end is also a common end. We could use our molarity to find the liters, for example, which would be moles divided by molarity, which would really be moles divided by moles per liter, so that they cancel, you end up with liters. The other common ending as well is actually to solve for the molarity, which is moles per liter. So a lot of times you use the stoichiometry to get to the moles part of it. And usually in the problem, they'll sort of give you the liters part or the volume part, and you basically just plug it into the molarity equation at the end. So it's very common steps here for solution stoichiometry. The incorporation of molarity either at the beginning, the end, or both is again a very, very common approach. Any questions on any of that there? I think we finished with an example last time. So I think we're on this example, if I'm not mistaken. So we want to work out this example here, which is where we want to calculate the mass in grams of calcium carbonate. So we'll look for the grams here of calcium carbonate. That forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of 0.15 molar sodium carbonate. So we'll do the equation here together. We're taking basically calcium nitrate and we're reacting it with sodium carbonate. Once again, you should be able to look at this and see a positive, negative guy, which means this is a double displacement reaction, which means the two positive guys, again, should switch partners. We're nice enough to tell us one of the products so we can make sure we get the right formula, but that is because calcium is +2 and carbonate is -2. That gives us calcium carbonate here, which is a solid. And then the sodium is +1, the nitrate is -1. So the proper formula here would be sodium nitrate that looks something like that. First off, any questions on getting the formulas there on the right side? All right, so why don't you continue on with the rest of the calculation, including you'll need to balance, obviously, this equation. And let me put up here some numbers you might need. Calcium is 4008. Carbon is 1201. Oxygen is 16. I don't know if you need nitrogen, but I'll put it up there, 1401. And not sure what else is left. I think that's everybody. Carbon, nitrogen, oxygen, calcium. All right. All right, so take a few minutes here or so, go through those steps, and sodium, I guess, was the other one. Determine, what type of problem you're doing, see how you're doing. So obviously we started with making sure that we wrote out the correct formulas for the equation. Clearly, as we've done on many stoichiometry problems at this point, none of it works unless it's balanced, which this one is not. So obviously, I think we just need to put a 2 there, and I think we should be in good shape. The next thing we want to think about is the type of problem that it is. In this case, we're mixing 25 milliliters of 0.1 molar calcium nitrate with 20 milliliters of 0.15 molar sodium carbonate. Is this a basic stoichiometry problem or a limiting reagent problem? It is a limiting reagent problem because when we have molarity, which is our moles per liter, in this case, we were given the molarity. We weren't given the liters, but we were given the volume. So we definitely could get to moles of each of these guys. And once again, that does tell us that this is a limiting reagent problem. So we do need to make sure that we figure out the limiting reagent before we could actually solve the problem. The next step really is still the same step. It is still, we're going to convert our guys into moles. So I'm going to do that up on top here, I think. So we will take our calcium nitrate. Maybe we'll take our calcium nitrate. All right, so our calcium nitrate moles here will equal the volume, which we do need to convert into liters. So once again here, that's going to be 25 milliliters divided by 1,000. To a liter gives us 0.025 liters. While we're here, we'll do the other guys as well. 20 milliliters, also divided by basically 1,000, or move the decimal place 3 places to the left, gets us that. So taking the volume for calcium nitrate, which is 0.0250 liters, once again, we're going to turn the big M into our moles per liter so we can see both units. So that gives us 0.1 moles per liter of calcium nitrate. And that's going to get us 0.025 times 0.1, 0.0025 moles of calcium nitrate. We'll do the same thing here for our sodium carbonate. And that's going to be 0.02 liters times the molarity, again, using both units there so we can see them. Moles per liter. Sodium carbonate there cancels, gets us 0.02 times 0.15, 0.003 moles of sodium carbonate. So once again, these are our starting amounts of each of these things. Any questions first off on that calculation there? I'll just kind of get that out of the way there. All right, so now that we have the starting amount, we're going to do a calculation to determine which one is our limiting reagent. So get rid of some of these here. All right, so what I'm going to figure out is if I want to use up all my calcium nitrate, how much sodium carbonate is needed. So I'm going to take the amount of calcium nitrate in moles that I'm starting with, 0.0025 moles of calcium nitrate. I'm going to do the mole to mole relationship between these two guys, and it is a 1-to-1, makes it nice and easy. So 1 mole of sodium carbonate is needed to use up our calcium nitrate. That means that we need 0.0025 moles of sodium carbonate is needed. Once again, we then want to take it and compare it to the starting amount. And do we have enough sodium carbonate? We do, just barely, but we do have enough of it. So that means that the sodium carbonate here is our excess reagent, and the limiting reagent here would be our calcium nitrate. Any questions on that? Once that we have the limiting reagent, we now could go back to the starting amount of our limiting reagent and do the actual calculation that we're looking for, which is 0.0025 moles of calcium nitrate. From the equation, we will do the mole to mole relationship between calcium nitrate and calcium carbonate. Once again, they will not always be a 1-to-1. So this would be 1 mole of calcium carbonate gives us 1 mole of calcium nitrate. That's going to cancel. If I got an answer here, it would be in moles of calcium carbonate. But again, we do want grams, so we might as well calculate the molar mass there of calcium carbonate so we can finish the calculation. So calcium carbonate would be 4008 for our calcium, plus 12.01 for our carbon, plus 3 times 16 for our oxygens. That gives us 3 times 16 plus 12.01 plus a 4008, about 100.1 grams per mole. So we'll use that as sort of our final step here. We do want to end up with grams, so we're going to put grams up on top, moles on the bottom of calcium carbonate. The moles will cancel. And that basically is that times 0.0025. We are going to get 0.250 grams of calcium carbonate would be produced in this case. That would be our theoretical yield in this particular reaction. First off, any questions on any of those steps there? Again, if you kind of look at it, it is still the same steps we've been talking about. We have our balance equation, we have our convert to moles, we have our figure our limiting reagent out in this case, we have our mole to mole relationship, and our convert our moles to some other unit. So again, still really the same 4 steps, just some integration of molarity, volume, and moles. Any questions on any of those steps there? Okay. So next thing we're going to talk about is really neutralization reactions and really sort of titrations as you started last week, and we'll continue your titration journey here today. Neutralization reactions specifically are those acid-base reactions that we talked about. And whenever you take sort of an acid and a base, you basically get 2 things. You get water and a salt. A salt is just an ionic compound really made up of those spectator ions in the reaction. Water is pretty much always the H plus from the acid and like the OH minus from the base. So that's basically how we get to the water part of it. Now, the fundamental change that occurs whenever you take a strong acid or strong base, like we talked about when we talked about different types of reactions, is really the formation of water. So that's one of the reasons why a reaction takes place. And that's really what's happening in these type of reactions. So regardless of what sort of acid-base combo you choose, you know, if you took something like HCl, which is a strong acid, and sodium hydroxide, which is a strong base, it is a double displacement reaction as it falls under that sort of umbrella. Our H goes to the OH, our sodium goes over here. We end up making our water and our sodium chloride. And if you did your total ionic equation, you would have H plus Cl minus, as that's a strong electrolyte, sodium plus some hydroxide, also a strong electrolyte. Water will stay together because it's a liquid. Remember, liquids, gases, solids, they all stay together. Weak electrolytes as well stay together. And sodium here and chloride. Once again, it is the chloride and the sodium in this example on both sides. That's our spectator ions. That leaves us our net ionic equation that we see there, which once again is the formation of water in this particular case. So all titrations, acid-base type titrations, this is basically these type of reactions. So titration problems are where it says, hey, you neutralize this acid with the base or the base with the acid. These are all really solution stoichiometry problems. As you saw when you did some titrations, titrations is a very common, and I lost the slide that's on your notes, but I'll kind of talk about the titrations. Is a very common procedure that we do that's used in solution stoichiometry. And usually in a titration, you add a known solution to an unknown solution. And you try to figure out a couple of things. A lot of times you may try to figure out the concentration of that unknown solution. Maybe you'll figure out the volume needed to neutralize it, something of that nature. So for example, if we talk about the titration you did the other day, you use a burette, right, which is that long glass tube. It has the stopcock there, right, which opens it and shuts it. As you know, right, it does increase the volume as you go from the top down. So if you're somewhere in this region, it's like 1.50 milliliters. Usually 2 decimal places is what you record off of a burette. In our example, in our titration that you did, you took some sodium hydroxide and you put it in there. In the case of the sodium hydroxide, it actually was your known solution when you did the titration. It will also be your known solution today. You know the molarity of the sodium hydroxide from the bottle, or I guess it was the box in that case, right? And you also know the volume of sodium hydroxide that was used in each titration. And whenever you do a titration, I'm sure you were told to take a initial and final volume reading from the burette. Otherwise, you wasted your time, yeah, if you don't have those numbers. So you do always want to take a initial and final volume, because when you take the difference of that, in our example here and in your lab, that is how you find the volume of sodium hydroxide, by taking the final minus initial. In our titrations that we did, we threw the acid. So you were using HCl last time down there in the flask. You also had your little stirrer, I think. You also put some water in there, which didn't make a big deal. But really important was you did put an indicator in there. And in the case of the titrations that you guys use something like phenolphthalein, I think. Yeah. And that is a acid-base indicator that actually works over a pH range. It works from like 8.3 to 10. Around 8.3, it is colorless. Yes. Around 10 or so, it is definitely pink. And there's various shades of pink heading into a pH of 10. You're usually told, I imagine, you want to hit the lightest color of pink that stays. Yes, is usually what you should be told in most cases. And that's because that will put you kind of over here, because when we do a titration, we typically want to titrate until we reach what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where exactly the moles of the acid equal the moles of the base. So that is really what the equivalence point is. And ideally, the indicator that you choose should change color near the equivalence point pH so that you could visually see I should stop my titration. It like turn pink, it's no more colorless. So for example, what that means is if we're doing the titration that you guys were doing, and really the titration you're going to do today as well, when you had your HCl plus your sodium hydroxide, plus you made water and your sodium chloride. When you reach the equivalence point, pretty much all the acid moles that were there have now been used up by all the base moles that's there. And pretty much the only thing you got left in that beaker or flask is basically water and sodium chloride, which is a salt. Water is technically neutral-ish, and sodium chloride is actually a neutral salt. Really, it's just sodium ions and chloride ions floating around at that point. It won't affect the pH. It'll be like a pH of 7-ish at that point. That's why it's also called a neutralization reaction. We basically make water at this point. There's no acid or base sort of left in a sense, as it has been basically neutralized. The reason they again tell you to go for the lightest color of pink is because your equivalence point is usually, truthfully, in the case of the last titration, should be like a pH of 7, a little bit below 8. And then the one you're doing today will be about 8-ish or so, is really where the equivalence point is. So if you get that really light color of pink, it should mean that you did stop your titration pretty close to the equivalence point. And usually when you do a titration, you want to stop it, is sometimes referred to as your endpoint, which is basically where you lay up your titration and call it a day. And if you do a good titration, your endpoint and your equivalence point should be pretty close to the same spot. If you do a crappy titration, they're pretty far away from each other. Now, some of you might have noticed this, and maybe some of you even said this when you did your titrations the other day. You know, I just added 1 drop and it went like super pink on me, right? Did anybody say that? Yeah, maybe, yeah. I don't know what happened. It was like colorless and then it went like super pink on me. I just added 1 drop. And the reason why that happens is when you do a titration, and you'll learn about this in 1B, but if you graph a pH versus, say, the volume of sodium hydroxide or base that you're adding, when you do the pH, it originally starts acidic because you're starting with the acid. And as you add your base, it starts to get a little bit more basic. And then you get this, which is known as a titration curve, is what this is. So at the beginning of your titration, you pretty much have, like the one you did there, acid, which is why the pH is low. As you start adding the base, we start to see the pH jump. Your equivalence point would be, you know, somewhere in this ballpark. That'll be the equivalence point where technically your titration is done. Let's just say for the last one, that is like maybe a pH of 7. Up here, maybe like a pH of 12 up there, which is a pretty big change in pH. So the reason why what happens and why sometimes people say that or you see that is really to do with the indicator. And the indicator, as I mentioned, works from a pH of 8.3 to 10. And again, it's colorless over here, then super light pink to really dark fuchsia pink, which is way over here, closer to a pH of 10. So as you're doing the titration, you should see the pink kind of stay a little bit longer, go away, stay a little bit longer, go away. And that's how you know that you are sort of getting to the equivalence point. So let's just say your thing turns pink and you just added like 1 drop and it went like super pink. So the equivalence point's here, and maybe you added 1 drop and you're up here, and maybe say that's like a pH of 10, right? Which means my indicator is going to show me really pink, right? Even though before you added 1 drop and you were, you know, back down in this region over here maybe, and it was colorless. Is there really a big difference in terms of the volume for the equivalence point between here and here? It is not, because as you go towards the equivalence point in titration, the volume doesn't take a lot of volume to change the pH a lot. So it goes pretty vertical, which means the difference between here and here in terms of volume is not a lot, right? So if I wanted the volume at the top there, so if I wanted the volume at this spot, I would just go straight down, which is basically there. If I wanted my volume at the equivalence point, I would go straight down, and it's pretty much the same volume, right? Now, that is why in the experiment, and really the truthful thing is, it really doesn't matter about the color. In most cases, the more important thing is, like the experiment says, that the volume of sodium hydroxide you add between the different trials are about the same. It's really more important than having the color being super light pink. Why people tell you that, you need to get the lightest color pink is because one drop difference between here and here can make your indicator go really dark pink, right? Which is, did you really miss the equivalence point volume by a lot if you added one drop or two drop too many? You didn't, even though visually it went from colorless to super dark pink. But the reason why they tell you to do that is because if I was not careful and titrated like I did when I went to school, I just opened that thing up and let it drip all the way down, look at my clock, and then shut it off at some point, right? Halfway full or empty. I could get that same color pink that I saw way over here, way here. As a pH of 12 is going to be the same pink, which means now did I miss my equivalence point volume? There's a very big difference between those two. So sometimes people get really hung up on the super light pink. It's not really that important, to be honest with you. Really, the volume that you're adding for every titration trial that you do is actually really more important, that they are equivalent to each other, because that probably will put you in the right spot. If you're careful. If you're not careful and you just open up, shut it, open up and shut it, you will be all over the place. So, you should really try to get the light color pink, but the equivalence in the volume is really the more important thing if you are careful. And that's why when you add one drop and you see a really big change in the color, it is because you don't need a lot of volume when you get close to the equivalence point to change the pH a lot. And because the indicators work off a change of pH, you could actually change the pH by a lot by just adding a drop or two, and that causes your solution to go from like no color to super dark pink. Any questions on that there? Yeah. Now, of course, if he told you that you should get light pink, you should shoot for light pink, but truthfully, make sure the volumes are equivalent. That's really more important. Any questions on that there? All right, so that was the backstory of the titration experiment there. All right. Let me clear this off so we can take a look at it. So let's take a look at an actual titration problem here together. And this is really a titration problem. And what is the volume of 0.15 molar nitric acid that's needed to neutralize 45 milliliters of 0.55 molar KOH? This is sort of how you know it's a titration problem. A lot of times they'll just say neutralize or something like that with an acid and base. So if we were to work problem, we do want to start with our normal, we want an equation, and we will start with our acid, which is nitric acid here, plus our potassium hydroxide, which is our base. Once again, that's a positive, negative, positive, negative. So our two guys are going to switch places, and we're going to make water like we talked about from really the OH and the H from the acid and the base. And we're going to put together the salt part from the others, which would be our K plus and nitrate, which should give us KNO3. So just like any other stoichiometry problem, you want to make sure you're starting there with your balanced equation. And now that we have it, it obviously is balanced as well. We're going to pull out the information. So for our nitric acid, we're actually looking for a volume. We do know the molarity of it, which is 0.15 molar, or 0.15 moles per liter. For our KOH, which is our base, we do know it is 45 milliliters. And we do know the molarity is 0.55 molar, or again, 0.55 moles per liter. So in this particular case, it is really a basic stoichiometry problem, because from this information, I could get moles, but obviously from this information, I cannot. So we can definitely get to moles from the one, but not the other. So it is just going to be sort of the basic steps. We don't have to worry about limiting reagents in this case or anything like that. So ultimately what we're trying to get to is we're dealing with the molarity of the nitric acid, which would be moles per liter. And if we look at this, we obviously already have the molarity given to us. We are looking for the volume, which means the one thing that we're really missing for the nitric acid is the moles of the nitric acid. So the moles of the nitric acid is going to come from the stoichiometry part of the calculation. And the only way that we could kind of do the stoichiometry part is we could get the moles of it. So that's the first thing that we want to do. This balance, we now want to convert our KOH into moles. We do need to, once again, convert our volume into liters. Whenever you use volume and molarity together, it does need to be in liters unless you're doing a dilution equation. And that would be 45 divided by 1,000. We're going to move our decimal place 3 places to the left, 0.045 liters. And now that we have that, we could do our moles of KOH, which would be our volume, timesing it by the molarity of the KOH, which is 0.550 moles per liter. The liters will cancel, and that will get us 0.045 times 0.550, 0.02475 moles of KOH. Remember that we don't want moles of KOH, but we do need moles of the nitric acid to get us to the volume. So this is where the stoichiometry comes into play. From the balanced equation, we could see for every 1 mole of nitric acid, we get 1 mole of KOH. So again, it won't always be 1-to-1, but that makes it not too bad here. So using our stoichiometry from our equation, moles of KOH. 1 mole of KOH gives us 1 mole of nitric acid. Gives us 0.02475 moles of nitric acid. That now is the top part of what we need. We already have the molarity. So now we're using stoichiometry, we're able to figure out the missing piece. The last step is to use, write it up here, the molarity here and solve for volume. So volume of our nitric acid would equal our moles divided by molarity. So we have our molarity and we now have our moles. So we will do that. The moles of it is 0.02475. Again, using the molarity where we can see both of the units, 0.15 moles on the bottom, liters up on top. The moles will cancel out and we will end up with here 0.165 liters of nitric acid, which if you multiply by 1,000 milliliters a liter is about 165 milliliters of nitric acid. You could actually leave it in either, as I do not believe it asks for anything specific in terms of the units. So titration problems are really nothing more than stoichiometry problems involving a molarity and volume. And again, even in this example here, you can see the same 4 steps. Balanced equation, convert to moles, mole to mole relationship, and convert those moles to some other unit. Any questions on any of those steps there? Okay, so why don't you try one then? Not that. I think I passed it. Or did I skip a problem? I feel like you have one more on your paper. That side, I don't have it. All my slides disappeared. You should have one with sulfuric acid, I think. Yeah, on your paper, your notes. Anyone? So why don't you work on that one when you find it here, and I'll punch it up here what it was. Yeah, from the notes on Canvas, you should have a different example there. It is, where'd it go there? Let me write it up here for you. All right, you should have, I believe this one, what volume of 0.5 molar sodium hydroxide is required to neutralize 125 milliliters of 0.5 molar. All right, so let's give that a try. What volume of 0.5 molar sodium hydroxide is required to neutralize or react 125 milliliters of. Okay, let's take a look. So once again, we're going to neutralize or completely react or titrate. These are really words. You sometimes see in problems, which basically means just a stoichiometry problem. So we'll start once again, like always, with the balanced equation. So we're going to take our acid, which in this case is sulfuric acid. We're going to add it to sodium hydroxide, which is our base. And once again, the H and the OH is going to make the water. And the sodium and the sulfate will come together really to make our salt, as it is really a double displacement reaction that's taking place. So we will get our water. We do want to make sure we recognize that sodium is +1 and sulfate here is -2. That is why sulfuric acid has 2 H pluses attached to it to balance it out. So that means that when we put it together, we do get Na2SO4 as the proper sort of formula for sodium sulfate. Any questions on that there? Obviously, we do want to also make sure that we are balancing this guy up correctly. And at this point, it is not balanced. Get rid of some of these extra things. So to balance it, it does look like we need a 2 there, I believe, and a 2 there to balance it. So that should balance it up. At this point, once again, here, we're actually looking for the volume of sodium hydroxide. We do have the molarity given to us of 0.5 moles per liter. For our sulfuric acid, we have our volume, and we also have our molarity of 0.5 moles per liter. Once again, we only really have the capability at this point to get to moles of that guy, which means it is just a basic stoichiometry problem. Much like the previous one, we're going to use our molarity for our sodium hydroxide to calculate what we need, our moles per liter. So we have the molarity given to us. This is what we're looking for. So we're going to use the stoichiometry here to get the moles of sodium hydroxide. So starting with our volume that we do need to convert into liters, we're going to divide by 1,000. And that's going to give us 0.125 liters, 0.125 liters. We're going to times it by the molarity of the sulfuric acid, moles per liter of the H2SO4. That gets us 0.125 times 0.5, 0.0625 moles of H2SO4. Once again, though, we are missing the moles, not of the acid, but the moles of the base. So that is where the stoichiometry and the balance equation is going to come into play. And we see it is a 2-to-1 relationship from the equation. And that's also why it's important to write the equation. So we'll do that. It is 1 mole of H2SO4 and 2 moles of our sodium hydroxide. That is going to get us into moles of sodium hydroxide. So we'll times it by 2. 0.125 moles of sodium hydroxide. At this point, we now have the moles from the stoichiometry. We have the molarity that was originally given to us. So we could solve for the liters, which would be moles divided by the molarity. Using dimensional analysis here, 0.125 moles of sodium hydroxide. We're going to divide by the molarity, which would be 0.5 moles per liter of sodium hydroxide. The moles will cancel and divided by 0.5 gets us 0.25 liters of sodium hydroxide, or if we multiply it by 1,000, 250 milliliters of sodium hydroxide would be needed in this case. Any questions on any of those steps there? Once again, that is step one, convert to moles, mole to mole relationship, and convert our moles to some other unit. Any questions? Now, cautionary note on doing titration problems, and sometimes taught to people, is an equation that we saw earlier, which is our M1V1 is equal to M2V2, which is the dilution equation, that you could use it in titrations. And some people even call it the titration equation. And it's really not, in a sense. It is, you only get lucky if you have a 1-to-1 mole-to-mole relationship like here. So if you use it in there, you get lucky just because you got lucky, because the stoichiometry is 1-to-1. If you tried to use it in this equation, our problem, you would be wrong because you have the wrong mole-to-mole relationship. So sometimes people, or you look up on the internet, will tell you that is the titration equation. I won't argue. It does work in a specific case of 1-to-1, but definitely in any type of titration problem, stoichiometry problem, you should always do the stoichiometry part, the balancing the equation, the mole-to-mole relationship, because people sometimes will just blow with that equation, and he definitely will get it wrong because you don't have the right stoichiometry to the mole-to-mole relationship. So remember, I would say that is only really the dilution equation, and also really the only equation that you probably should be using if you wanted to, milliliters and molarity together. Other than that, like we talked about, you should not use milliliters and molarity together. You should definitely use liters and molarity always. Any questions on that there? Now let's try one more here and finish up our titration journey here. Let's say we wanted to know if it took, I'll just go with 32.5 milliliters of 0. I don't know, 723, just making up numbers, molarity. We'll do calcium hydroxide. To reach the equivalence point in a titration of we'll do I don't know, we'll do about 57.5 milliliters of, we'll do HBr, which is a strong acid. What is the molarity of the HBr? All right, so take a couple minutes, follow the steps that we've been doing. You can consider calcium hydroxide for this example a strong base, and HBr is a strong acid. So follow the steps. In this case, we're actually looking for the molarity at the end of the hydro. So obviously this is a titration problem. We're looking to reach the equivalence point where the moles of the acid really equal the moles of the base. So we'll start out with our equation. So we'll take our acid. We'll react it with our base, and once again going to do our double displacement. We for sure know we're going to make water, which comes from here and here. That means our calcium and our bromide would come together. Again, calcium is +2, Br is -1. That gives us a CaBr2 as the proper formula. We then need to balance it. So I believe a 2 there will do it, and a 2 there should do it. At that point, we have our balanced equation. Any questions on writing those equations there? All right, at this point, if we take a look really at the information given to us, it will help us with our approach. In terms of the calcium hydroxide, we do have the volume. We do have the molarity given to us, which is moles per liter. For our HBr, we are looking for the molarity, which is moles per liter, but we do have the volume given to us. So really, we do have the bottom part. We just need to convert it to liters. So the stoichiometry is going to allow us to get the top part of what we need, which is the moles. So we definitely could get moles of this guy here. We will convert our volume into liters using our 1,000 milliliters is a liter, or again, move your decimal place over 3 places. So using the volume of our base and the molarity of the base that was given to us of 0. What did I make up there? 723 moles per liter of calcium hydroxide. If I stop right at this point, I will now have the moles of calcium hydroxide. And if you want to get a number, you can. If you don't, you can continue on with the calculation too. And if I did get a number here, I would have 0.023, we'll call it 50 moles of calcium hydroxide. We're not interested in calcium hydroxide because we do need to get over to moles of the hydrobromic acid. So that obviously is where the stoichiometry part comes into play. It is a 1-to-2 relationship from the balanced equation between those two. And if we do that, we're going to use 1 mole of CaOH2, gives us 2 moles of HBr. So we'll take that times it by 2, going to get us 0.04, we'll call it 70 moles of HBr. That really is the moles part of what was missing. So we do have the volume here. So we do want to convert that as well into liters. So we do our 1,000 milliliters as a liter. 0.0575 liters. Now we have everything we need to calculate the molarity of the HBr. So our moles, which was 0.047, our liters, which was 0.0575. And if we divide it there, we end up with, we'll call it 0.817. The units here would be moles per liter of HBr. Or you could write, if you like, I'll put it over here, 0.817 big M HBr. So you could obviously report it that way if you like to do it that way as well. Any question on any of those steps? Once again, I don't know how many times I could repeat it though, still the same steps. 1, balance equation, convert to moles, mole to mole relationship, and here using really molarity to change our moles into what we're looking for at the end. Any question on solution, stoichiometry, titration type problems? That is really the calculation that you do for last experiment and today's experiment, pretty much this experiment here. Any questions on any of that there? All right, we will lay it up there for today.